Welcome everyone to part two of this refrigeration design using distributed piping software. Lots of great information last week. As you can see, James went in deep on how MicroPipe works on doing a whole cold room. And he did it very fast. Like, it's always surprising when I watch him do that. As an engineer, there, like he said, there's a lot of work up front where you're drawing it out, making sure you got your pipe runs and your networks and your terminations done and your loads. But after that's done, when you put that into the software, it can be done really quickly, which I really enjoyed. And part two today, we're going to get into the impact of incorrect sizing and refrigeration pipework. And what's really cool about that is that I've seen this a lot as a technician in the field, and I didn't notice it. And I didn't know about it because I didn't know enough about refrigeration at the time that it was actually a piping issue and not, well, it's a system issue as well, but not really the technician side of the system issue. So we're going to get into it and get an understanding how using a software like this could reduce that factor. James, how you doing?
I'm good, Trevor. Welcome everybody. Good afternoon, good morning, depending on where you all are. Really looking forward to tonight's session. I've actually pre-prepped my calculations for this evening because once we've been through a presentation, a lot of the information I'm going to be playing around with system penalties, looking at different velocities, just going through what makes an efficient design, what would actually constitute a poor design. But because MicroPipe as a software, great software, the big strength of it is it knows that the systems and the connected loads, it's a dynamic system, so it recognizes this. So, but like any software, it's only as good as what you put in. So hopefully tonight I'm going to be spending a little time just explaining perhaps and enforcing some nuances to occur just to help you guys out when should you start using MicroPipe. One thing I'm just going to say, Austin, I owe you an email. I've looked into the question that you've asked me, and early next week I'm going to get you a real good response out, so don't think I'm ignoring you. So
appreciate it.
No problem. Without further ado, I think I'm just going to crack into the presentation.
Looks good.
So as Trevor said, welcome to mini-series part 2. I think those who aren't from the UK will be pleased to know after tonight's session, I'm really going to be concentrating and doing the demonstrations based on imperial units of measure, based on BTUs. This is going to be the final one with a synthetic refrigerant. The next 3 sessions, we're going to be talking future systems, current and future CO2 systems all the way, and how to select pipework and how the software sizes pipework. So first few slides, a little bit repetitive, but we don't know who's joining us, you know, people who are new to the system. So a little bit of an overview of White Rose software. Taking the first slide away, but just to reiterate, the software was developed by my mentor, Ian Ramsey, who sadly passed away about 3.5 years ago. When he passed, his family, you know, it was a wish, can we make the software continue? And I'm far from an IT specialist anyway. I worked with my IT partner, and by hook or by crook, we got it going, and it's remained ever since. And we're entering a period of modernization for the software. It's how long's a piece of string. I'm working with 120,000 lines worth of code, and I'll be working with a developer who understands the code but doesn't understand the calculations. So it's going to be quite complex. It's going to take some time. Anyway, in terms of the use of MicroPipe, conservatively, just in the UK, we believe that there's at least 30,000 systems, all the way from humble condensing units all the way up to big centralized rack systems. And this is just supermarket systems as well. So it's the software of choice for contractors and consultants in the UK, and features in specifications of retail supermarkets. So MicroPipe, it calculates lines based on user-defined parameters. The lines that it can size: suction lines, liquid lines, which we'll be concentrating on today, discharge lines, liquid drain lines, relief and vent lines, and also valves and bends can be added to each circuit. I always do that as a matter of good practice. Today's demonstration is going to focus on MicroPipe, on using MicroPipe to design systems for efficient suction lines and for good oil return, and also appropriate size liquid lines. I'm just having to move the ribbon around a little bit. Sorry, everybody. I'm going to concentrate first on the suction lines and the importance of oil return. So in supermarket applications, the capacity of the system varies. It's very dynamic. As we know, in winter, there's not a great deal going on. We've got good energy consumption. That can also be a problem. If you incorrectly size, you could end up with oversized pipework. MicroPipe compensates for that. The real problem in designing suction line pipework, especially if you're not using MicroPipe and you're working from charts and working from first principles, is grabbing a hold of that dynamic factor. So for example, risers, vertical pipework, under low load conditions, really important that it's sized appropriately. So we're going to get that oil return under all conditions, as well as in the middle of summer on full design conditions. So the software will calculate single risers, but it will also size double risers, which is a real good feature, especially for if you've got to run big island configuration of frozen food cabinets, you know, where it's a little bit of a numb load, little bit static, but when things come off a defrost, when things are satisfied and there's not much load called for, still really important to get that oil back, and it can be a problem if we don't, and I'll touch on that on the fourth bullet down. So effectively, the main case is designing suction lines using MicroPipe enables good oil return irrespective of system load. Poor suction line design can result in oil not returning under low load conditions, but often that won't manifest itself. That oil return, that problem, that won't become apparent. You know, a lot of systems that are being commissioned up in summer, run up in summer, hey, there's a good duty, good load on there. These systems are going to run, and the contractor is going to move on to the next job. That brings me on to the last point. Inappropriate size suction lines, oil risers, it can result in excessive service call-outs to compressor oil faults. The problem here is, why would a technician, when they attend site, they see an oil fault, they're going to do something about that. That thing is generally going to put possibly low on oil, put some oil in. It's going to clear that alarm, and they're going to go to the next job. The problem is they wouldn't know. You know, they're not from a design background. You know, these guys, technicians and girls, these guys are incredible. You know, they're keeping the supermarkets cool all year round. These people are so busy. We need to work to support service technicians. We don't want to leave them thinking, well, what else is going wrong? What else is going wrong? Ultimately, you get too much oil in that system, you know, and it's an oil problem. We're going to look at adjusting defrost settings. Eventually, we're going to get that oil back, and then all of a sudden, that technician realizes there's too much oil in the system, you know. But it was never a consequence of that technician. It was a consequence of an inappropriately sized suction riser. Conversely, suction line risers are too small. The velocity turbulence for suction gas and resultant oil can impact on efficiency through additional pressure drops in the system. So that's often the trade-off. If you're designing a system, a distributed system, and you're not using the software and you're using a single line size calculator, or and then built off charts and first principles, and you're building it all up into a jigsaw. Very, very difficult, because with each additional line, you're introducing another line loss, or you're introducing further duties, further loads on the system. So an old school comp said to us, well, let's just drop, if I'm running a horizontal line, for argument's sake, and it's 2 1/8 inch, let's put 1 3 inch, maybe 1 5 inch vertical riser up. Yeah, that's going to increase velocity, and they're going to, as a designer, you can see over that one line what the velocity is going to be, but not over a dynamic part of the system. And actually, if we've got incorrect sized risers, if we're speeding up the velocity, and I'm going to talk in metric here, we've got 20, 25, 30 meters per second, we're incurring pressure drop within that system. We're going to increase system losses, and ultimately we're going to introduce inefficiencies in the system, which is the last thing that we want to do. So MicroPipe, it allows a designer to analyze the results of calculated data and adjust pipework diameter sizing to reduce or increase velocity to ensure good oil return all year round, whilst minimizing pressure drops. So this is quite important, because as a designer, what I've always been taught, again, working in SI metric units, is when I do a MicroPipe calculation, the evaporating temperature is the lowest, the input is the lowest temperature that corresponds with the evaporating temperature of the display case. Ultimately, we know that the saturated suction temperature when we get to the compressor is 2 degrees lower. So we allow 2 Kelvin line loss from exit of evaporate, from the point of evaporation all the way through. I've seen systems that I've run through in the past which haven't been designed using the software, and there's been problems in summer. Oh, this plant's appropriately sized. It shouldn't be struggling. What's going on? The problem being is that it's actually not the plant selection. It's the pipework. It's the pipework sizing. And if we've got small lines and we've got big penalties, big losses, we could actually have 4 Kelvin in that line. And for every degree out, we're incurring 4% energy hit, but also we're making that compressor actually work harder and the system work harder. So irrespective of the plant being appropriately sized. So just a little bit about designing on the theme of efficiency. So MicroPipe works on the premise, again, of user-defined parameters. Typically, a target total suction line loss penalty, said previously, is 2 Kelvin from the evaporator to the rack suction header. MicroPipe allows a design engineer to set the penalty at anything. So though a 1K penalty, as an example, will increase the main suction line pipework and ultimately cost, because we're going to have potentially larger size pipework, the system will operate with a reduced penalty, promoting energy efficiency. If we size distributed suction lines from charts, it is difficult to calculate their overall penalty due to the dynamic nature of refrigeration systems. Just again to reiterate, this is something that the software considers. So often systems designed through charts and first principle calculations can result in excessive losses and penalties, and these impact energy and performance. But more crucial than that, from a design engineer's perspective, it takes a hell of a long time to get your old charts out, to get your ASHRAE books out and looking at formulas and work out from start to finish in a distributed system how to size the pipework. Now, I know, I've been based in the UK all my life, but what I've found out recently is in the US especially, there's a lot of stub systems out there, which effectively we've got multiple suction and liquids connected to a header on a rack. And I can see the merit in that. If you're sizing off charts, you want to limit the number of fixtures, number of display cases or room coolers that you have connected to that, to make the design process that little bit simpler. Designing on subsystems, although there's advantages, it's hell of an expensive way to do things, especially if we're talking large systems and, you know, anything up from convenience stores. You know, in the US, there's some huge stores out there, you know, Walmart's, what I'd class as hypermarkets. In the UK and Europe, you know, they're just a standard size store in America. So again, it's great. It's a great system, a great design tool to use, and you can actually benefit your customer through reducing installation costs.
So we have a question. Yeah, John, go ahead.
Had to find unmute. Good afternoon, James. So one of my questions, I noticed when you have up here, you got 2 Kelvin suction line loss from evaporator to compressor. So, you know, like you, I've been designing systems for about 25 years or so. I'm not sure how large your stores are, but have you ever had an opportunity where you had to increase that to maybe 3 Kelvin or 3 PSI total line loss due to the number of circuits and the size of the store to try to compensate so that, you know, you can continue with smaller line pipe?
Yeah.
Oh, okay.
I have, John, and I'll touch on that, and I'm glad we've sort of asked the question now whilst my head's in this. The size of stores typically, John, in the UK, supermarkets are 40,000 square foot. So they're probably what I'd class as a mid-sized store for an American supermarket. And different retailers have different philosophies. Most big box retailers have nowadays two booster MTLT CO2 packs. Asda a little bit different. Asda were part of Walmart, and they've generally got 4 packaged MT plant units and 2 low temperature units and a dual temperature. So to get to your point, John, I have come across this. So effectively, a supermarket chain can say, this is our layout, this is what we want you to design to. You design to that. 12 months down the line, they get an initiative and they think, oh, we want to add two 12-foot display cases here, and we want to add another cold room in the back, and we want to add this, we want to add that. And you're absolutely right, John. There are instances when I've had to go back into the software and I've had to tag in to an existing line at high level. And ultimately what that has done, it's had an impact negatively on the penalty. But MicroPipe does allow you to rework, so you can actually pick an existing calculation, you can rework it by putting additional fixtures on. Last year, I worked with your colleagues over at CBS in the central region in the UK, and we landed, what was landed was the first store actually in the world which was operating on an A2L in a distributed system. So everything in the store is on A2L. And what we had to do there is we had to run at 3 Kelvin. Effectively, we had to work around the limitations with a refrigerant which is mildly flammable. And yes, you need that perfect storm to actually ignite the refrigerant. We're still constrained by volume, and we work to a volume of 54 kilograms within a system. And effectively what we did to ensure that we wouldn't exceed the total volume in the liquid line, we actually tightened up the suction line, we tightened up, or we expanded. So we let go a little bit of efficiency to get smaller pipe working, just so we mitigated and we met the criteria as laid out by what we follow in the UK. It's a British standard 378 on refrigeration systems and heat pumps. So I'm happy to report there's been no adverse reaction. I'm a little bit detracted sort of this year, but I've certainly heard nothing, no negativity, considering we had two 40-degree-Celsius days last week in the UK. So I'm not sure. Hopefully that's answered your question, John, but feel free to pick up with me offline or Trevor.
It did. Thank you. I appreciate it.
Yeah, thanks, John. So just moving on to the next part of the suction line size, then we're going to touch on liquid lines a little bit. So there are two types of suction line riser, single and double. Single rise is obviously the most common, and let's be honest, no installation technicians really like and look forward to constructing a double riser. You know, there's a lot of joints, a lot of bends, time consuming. So we can see them in medium temperature systems where we've got a lot of display cases connected in a run or an island, or that final lift. If you've got a piece of plant on the roof and you've got to overcome that high level beneath the roof to on the roof, you know, you can maybe get a 3 foot 1 meter lift. That's again just assuming the rack is located above the sales area. So just a couple of images. You know, I'm sure we're all familiar with what oil risers look like. However, double risers, they are more commonplace in low temperature systems. Generally, I see them where you've got 6 fixtures connected to a riser. Double riser, as we said, can be required under low loads. As the suction volume is reduced, so is the velocity in certain suction pipe. The two risers are often a different size. So just put a notation there. So this is from my perspective. I'm not saying I'm right. You know, there's a lot of experienced people, much more experienced than me, you know, on this call out in industry. I generally target a velocity of 10 to 17 meters per second, or 1900 to 3300 feet per minute in riser pipe work, to make sure that it's adequate. So I know it's going to get the oil back at the low velocity, but it's not going to cause too much turbulence and impact on pressure losses within the system. Touching now a little bit before we go into the software itself, the importance of appropriate size liquid lines. So again, just to reiterate, system load varies and liquid lines have to be sized to ensure sufficient liquid refrigerant at the expansion valve at all times. Designing liquid lines using MicroPipe provides appropriate size liquid lines, though network lines must always be checked to ensure low line velocities. The software is awesome, but you need to know what the outputs are telling you. So it's not a case that you know, you could get a fresh graduate or a school leaver, you could teach them to use the software really quickly. That's not a problem. The problem lies in being able to analyze the data that it provides at the end once you've run the calculation. For me, to ensure we get appropriate size liquid lines, I set the design criteria at 1/2 or 1 degree Celsius. Effectively, what I'm looking for is MicroPipe's good at this. Never, unless you've got a super low duty connected, but in supermarket applications, add a fixture where you're brazing that liquid line to the cabinet and subsequent valve, which is downstream of the tail of the cabinet. You do not want to hit that valve at a velocity over 1 meter per second. Fortunately, the software allows that. It didn't used to. You had to be really careful. The reason I mention that is that's one of the big things with Danfoss, especially their electronic AKV valves. It's one of the first things in the manual. Make sure that to prevent liquid hammer, that you do not give liquid to that valve at a greater velocity of 1 meter per second. So as you know, the aim of the liquid line, we're looking to deliver a solid stream of liquid from the condenser or receiver to the expansion valves. Talking a little bit more about undersizing liquid lines, it can result in flashing before the expansion valves. This increases pressure drops and can also impact the desired refrigeration effect in the evaporator. In warmer months, undersized liquid lines will impact system performance, ability to maintain product temperature in display cases, or indeed cold room coolers. So liquid lines in supermarket applications, in my opinion, I'm not saying I'm right, this is just from my experience, should be no more than 1.2 meters per second or 235 feet per minute in network lines. Those are any line that aren't actually connected to the fixture. So the interconnecting network in between. And then no more than 1 meter per second or 197 feet per minute of the expansion valves. To reiterate again, high velocities will cause liquid hammer at the valve and will not be supported by the valve manufacturer.
So that's something interesting, James, because I see where you say 197 feet per minute. And when I was in school, and I wasn't in engineering school, just in trade school, in the different line sizing software books, one was from Garth Dennison, who built one here for North America. And it was in the liquid lines, they always said 300 feet per minute. You always want to keep it below 300 feet per minute. But I see here, depending on if it's a network, if it's a termination line, if it's a common line, that there is different numbers. And this is up to the engineer, I'm assuming, who designed it and just does it by experience.
Absolutely, Trevor. But as I said, it used to be a bit of a problem, but Ian ironed out those problems. So effectively in supermarkets now, you'll never encounter at the termination, at the point of cabinet, you'll never have a line size that is sized, or you shouldn't have a line size sized, which is going to be greater than 2 or 197 feet per minute.
Because I can pull out the book right now and it's a line sizing guide, and it says that. Does that make a difference? And it may not, because I'm still learning here, on the type of refrigerant. So like if it's R12 versus R22, or because they're out anyway, or HFO or CO2, it's the same for all refrigerants?
Yeah, liquid lines, yes. Now, I'll tell you what is interesting. And as I said, Trevor, I take an agnostic approach in terms of CO2, A2Ls. But a big positive with CO2 is due to its density, due to the high pressured nature. A lot of what we've discussed, so going back to suction line sizes, you don't often get those, you don't get low load problems and oil problems because the pipe work's much smaller anyway to begin with.
Well, there is a lot of oil problems, but I don't always necessarily know if it's from the piping, because what I've seen a lot of
problem. I think it's connected a lot of them, Trevor, with CO2 systems. We suffered in the UK a little bit with oil management into the compressors onto the rack themselves.
Because what I've seen and heard and talked with it, what a lot of end users do, and they put this either on the engineering or on the contractor, is that they'll size a system for a 2-year project. So let's get 25% of the system up and running right now, and 75% of the load is not there. So now the contractor got to figure out how to keep that equipment running, because now there's no load. How do you, as an engineer, and how would a software like this help something like that? Or does it? You know what I mean? Because I'm seeing this more and more where they know they're going to have future expansion, but they're just going to build a section of it now, but they want all the equipment in now. And I've seen this multiple times in plants, industrial applications, where they got 10, 15 compressors and they're running the system on 2 compressors because the load is so low, and then they run into oil issues because of that. And then the contractor has to keep coming back and back. You know what I mean? Is there anything that this software can help with that, or that is just complacency of that end user trying to jump ahead or not plan?
Yeah, but it's easy for me to say complacency here. But obviously, what you've just mentioned there, Trevor, that backs up similar to what John was saying. So it's possibly more of a thing than what I see in the UK. Generally, what I've always allowed for in certain parts of the system is a bit of a stub that's capped off and brazed up, which will allow for that future expansion, a couple of K sections. But as you're talking much bigger systems than what we have here in the UK. Now, what MicroPipe can do, you can run dual suction lines. So you can run suction lines in parallel with one another. Now, I guess that in itself, you're actually sizing for a specific load, but it's like the reverse of having a riser. Effectively, you can have a series of horizontal pipe work, so that would help. That would help support. But it'd be good to, I mean, it'd be really good to have a look at, if there's an example and how phasing occurs as well during construction, whether or not it's a refit or a new build. It'd be really interesting to look at from what's going on overseas, away from the UK, because I'm here to help. I just want as many people as possible to, reap the benefits of using the software.
Yeah. Okay. Thank you very much for answering that.
No problem. So just last point here, Trevor. So liquid lines, for me, they can be oversized with very little negative performance, though a system will require a great system charge, and in low ambient conditions, this will increase installation costs.
So I've seen, this is another thing that I've talked with a manufacturer about, where they ran into an issue where the sales guy or the salesperson for this manufacturer went out and said, okay, you can use a 5/8 line. So they went and did 5/8 lines everywhere throughout this building. But some of the systems only needed a 1/4 inch line, and they started running into issues because the liquid line was too big. Do you think that is because and I didn't know the full story and I didn't follow up with it, but it triggered my mind. Having too big of a liquid line would cause, you need more refrigerant, but is there any other cases with velocity now that if you get that liquid line too big, will your velocity drop off too much?
So there is a potential there, Trevor, if we're talking significantly bigger, where we might have to increase this, try to increase the system pressure. So inadvertently run a system inefficiently. Was that a refrigeration system you were talking, Trevor? Was it I'll tell you what, commercial. I often see this sort of thing with in the world of air conditioning and VRV systems. Where I kind of laugh about it, and it's everything's 3/8 1/2 inch, and there's not much in the way of sophisticated design that goes into them.
Yeah, because another thing that came up was that in some situations there are liquid line pumps, because if you got a 400-foot run that you need to move that, and because the velocity gets so low that you have to put a liquid line pump in there. But the cost of that is, I hear it's just astronomical at this point, to add that to a system. It just overcomplicates the system as well. But I think that's where oversizing could have negative effects as well, not only the overcharge. So, and engineers probably know this, something that I don't, it's not my wheelhouse.
Trevor, I worked for a guy, and I'd been in the industry long, so we're going back 18, 19 years. Real old school engineer, wouldn't use the software at all. And a lot of his sites, we ended up having to retrofit liquid amplification pumps, for the reason being you had a condenser in one corner of the supermarket and the plant room was in the opposite corner. We're talking 120 meters away.
Wow.
But in his mind, to the point John was making, so we're not necessarily seeing the big changes now, but historically we did. Supermarkets will be, well, we want to future-proof it. This is the initial concept. We'll see how we trade. So my boss was like, well, I'm not taking any blame here, because ultimately I've made sure that the liquid line is big enough for when additional load gets added onto that system. But you're absolutely right. What's happened there is, especially if we're talking big runs, which are unusual in a supermarket now in the UK, especially with F-gas. A lot of end users, there's been a big focus on getting your refrigeration plant as close as practically possible to the display cases, to the cold rooms. But when I first joined the industry, often you could have a internal plant room, which isn't really a big thing in the UK now. Great for service technicians, perfect conditions to work on. Nobody wants to work on the roof when it's raining. But ultimately, when they had more money, that's what retailers would spend the money on. But more often than not, you'd find the condenser in the complete opposite corner.
Real quick, That was interesting that you said, Trevor, that you saw a lot of 5/8" lines for the liquid line. In the US, depending on what kind of defrost they would use, if you got hot gas defrost, you would typically have a larger liquid line than you would actually need. So when you do reverse return and it goes through the evaporator, you want the liquid line big enough to get the gas back up the line so you don't increase the pressure. So
Yeah.
that could be one of the reasons why they
Yeah,
just
this
went
one,
with,
yeah, we have lots of, I think every system I pretty much worked on is hot gas. And yeah,
yeah,
you always want to have it two sizes up for the liquid, but
yeah,
I think this was more of like a small condensing unit with 4 or 5 cases, electric defrost.
yeah.
But
And then,
I understand what you're saying there, John. Thank you.
yeah, and then just one last point. The other thing I've ran into over my career is, software, line sizing tools, spoiling tools, all these tools are fantastic, but they can't overcome poor design. I
Yeah.
mean, when you land out a store, you got to have some wherewithal on how the system is going to be laid out, and how many loads or plants, as you guys would refer to, how many you put on a loop.
Mhm.
It has limitations, and
Yeah.
if you try to push it, there is no software out there that's going to compensate for that.
Yeah. Yeah. I love that.
John, I couldn't agree more. And just winding back a day from the days when I set up Amiga, I set up a consultancy some years ago, and I sold the company and exited last year. And to that point, John, the trainees I brought into the business, I didn't let them anywhere near the software for 3 years. I wanted to make sure that they truly understood a pressure enthalpy chart, how to plot it, how to understand and know what's going on in a system, and for them to understand what goes on in dynamic loads, not just at full design or in ultra low ambience. And you're absolutely right. The software, it's brilliant, and it saves so much time. But what it can do, there is a danger that you need to be experienced so you can check those outputs. And if you let a young aspiring designer loose with the software, they need to be mentored. They need to have somebody who can check and review the work so they absolutely understand what sort of velocities, what sort of losses they should look at, all the idiosyncrasies that we find in refrigeration design. So that's a really good point there, John. So, even being sort of custodian and owner of the software, I'm very big on offering one-to-one sort of trainings, especially for younger engineers. That goes without saying. So moving on a little bit, this is, real crude layout is this. So I've effectively shown an island of 4 display cases chilled, 3 on a wall, and then behind we've got 3 low temperature cabinets. And I'm just assuming that the suction and liquid lines, we've got a package plant, so we've got an onboard condenser. I've selected R448A as the refrigerant, and I'm glad I've done it this way. I was considering, should I build the isometric up so everybody can just see how quick the software is, but with all these good questions that have come through, I've actually prepared the MicroPipes. So I'm going to just move on to very quickly the next 2 screens. So the calculations that I'm working on, you can see the design inputs at the top of the screen. So I've shown on here the medium temperature and the low temperature pipework sketches, the isometrics. Coming down, I've got a common liquid line here. So without further ado, what I'm going to do, I'm going to stop sharing and I'm going to launch MicroPipe, and let's get into looking at some sizing.
I love that we do this as a live event. If anybody does have any more questions, I want to thank John for asking some. Please ask them, even if it's not super related to pipe issues. But we got James here who has been doing this for a long time and can offer support and really answer those questions.
What I think is great, Trevor, is just conversations with yourself and John participating. I haven't necessarily got all the answers or necessarily the right answers. So I love these forums, because you don't necessarily have answers, to every question. So all being well, everybody, can everybody see my screen?
Yeah.
So excellent. So this is effectively what we're looking at here is we've got 17 circuits on this medium temperature suction circuit. So for each one, I've started off, you've either got a network or a terminal. So anything that's connected to a display case, referring to the store layout plan I've just showed and the isometric. So this follows all that. So I'm putting in duties where necessary, the length, the bends, the valves, what number, because you have to, MicroPipe works on quite a simple logic. You give every piece of pipe a number, and it has to be a number. I've had a new user who got frustrated because the way that he'd actually numbered, he hadn't used numbered, he'd gone A, B, C, D, E, and obviously the software didn't recognize letters. He needs to recognize numbers. So once you've put all your information in, so we're going up, so network pipe work, so you can see we're carrying duty at that stage. Something I'm going to spend a little bit of time on in the next 10 minutes, oil risers. And I'm just going up just to show everybody. So we get to the end, and this effectively, we've got 7 cases. I've assumed each one has a duty of 5 kilowatts or around 18,000 BTUs. And overall, we're looking at a 2-inch suction main, and we've got a velocity of 6.84 and a penalty of 1.29. So really well below the 2 Kelvin. So I've done this deliberately because this is a nicely designed system in terms of efficiency. If I go on to design entries here, I've assumed we're evaporating at -6, put an arbitrary figure of 20 Kelvin, suction superheat, maximum liquid temperature 35, minimum liquid temp 5. So again, I'm assuming this is for a UK based store. So what I'm going to do now, I think what I'd just like to concentrate on, just come down and show you some of the riser sizes. So inch and 1, we've got a 11.3 meters per second. So we're well within the tolerance band that I look for as a designer. Again, 15 meters per second. And I think we've got one. Nope, they're the risers. I fixed all this pipe work. Now I'm going to unfix everything. And I'll show you what MicroPipe will do. I'm going to put, let's go 3 Kelvin. Let's assume this is equivalent of design using charts. It's going to give us an answer. It's going to give us what we're looking for in terms of, it's going to give a design within a 3K penalty. But hang on, look at this. We're on circuit 17, the last circuit. This is carrying 35 kilowatts. This is 7 cases. And MicroPipe has selected inch and 3. Now, those of us who design will recognize instantly. That's a problem. That's a problem waiting to happen. Maximum penalty, 2.58. We're well above. So we've actually, by default, we've created inefficiencies. We're going to have a very inefficient refrigeration system here, or suction line. So if I unfix everything, I'm going to go to a riser, and we might have what we're looking for here, by the way. So, just because I've put a high penalty in, it doesn't necessarily mean it's going to give me a garbage answer. Just looking at that, it's carrying 15 kilowatts, inch and 8, velocity of 1.48. Hey, I've got no problem with that per se. Inch and 3 main, I'm going to come down a little bit. Inch and 1 riser carrying 20 kilowatts, 15.31 meters per second. Hey, I'm good with that as well. But what I can't overcome, what I can't get over now is the fact that I've got this penalty here of 2.58. And it's all because it's effectively all because that I'd sized, I'd put maximum penalty. So I'm going to go for ultra conservative. I'm going to promote efficiency. I'm going to end up with some bigger line sizes here, 1 Kelvin. I'm going to hit the run key so you can see how quickly it sizes things. So for 5 kilowatts, and just let me see, yeah, we're on 448 as a refrigerant. It's actually minimum oil return. We're connecting at a horizontal level. So I'm not too fixated that its oil return capacity is 8% over in this instance, but let's just go through. I think the important thing here is to look at the maximum penalty. It's less than 1 Kelvin. So we know we've got quite an impressive system from an energy perspective, but is it everything that we're looking for as design engineers? So I go to, so this is carrying, I know it's carrying for display case duty. So actually the minimum oil duty, so when you select a riser, the actual minimum duty for this is, well, we've got 4. So, you know, we might only have 1 carrying duty at once. So effectively it's 25%. So look what's happened there. It's like telling me, hold on, I've got a problem. This isn't a problem. This is what I'm hoping to achieve with this. And I think hopefully it answers sort of some of John's questions in terms of using the software. In some respects, software is only as good as the engineer who's worked up a design. So 15 here. So I'm going to reduce that. That's so that I know that's carrying three lots of display cases. So I'm going to set that 33%. So let's see, it's still not going to let me run the pipe work. So I'm going to say, let's see if I increment it up to 1.2. No, still not having it. So you can see that MicroPipe itself, actually, it does think about things. And it's like, whoa, what's going on here? So I'm going to go 1.5 now. And we're still struggling. Now I know why we're struggling here. If I run at 2, let's take it up a little bit. See what's happened here, because I've insisted on a 25% oil return, and I've got 4 fixtures connected. So I've had a bit of a smile on my face because I knew this, it wasn't going to accept, it wasn't going to take, because MicroPipe is reading off ref prop, so it's reading pressure and temperature at various stages. So sometimes you can't necessarily input what you want to input because it just won't let you. But if you have a look as well, we've selected a 7/8 line here, and it's selected 7/8, and it's a 26.34 meters per second. But what I'm going to try to do now is, you know, well, if we're insistent that we want to carry that 25% minimum duty, so we can select a double riser. Hey, look what it's done here. So we've got an inch and 1 and a 7/8 riser. It's brought our velocity down. It's actually brought the penalty down a little bit as well. So I know circuit 15. That's quite a high. That's quite high. Is that? That's on the borderline of me maybe changing and, you know, dropping a size. So if I look at inch and 3 there, and it's dropping to 7/8. Let's increase the oil return to 40. Hey, look, it's automatically, it's auto selected. Actually got this little cool tool here, here as well. where it's selected Incheon 1, but we can actually go in and you can actually see the impact, you know, on velocity. You can see it increasing. And then once you get over 6K, MicroPipe will say, no, I'm not playing at that, but you get all this great information per circuit by picking the hand tool there. So in interest of time, what I'm going to do, so I'm going to work this back to what I consider is a well-designed system. So one that's efficient, I'm going to say 1 Kelvin. Let's really go to town on this. I'm going to reduce, I'm going to, so let's see what happens. So we've got a 0.93 penalty. We've got a double riser. We've only collected 4 medium temperature cases. Let's be fair, technicians installing, they ain't going to thank us for doing this, because rightly they'll say, I've installed thousands of systems like this and I don't need a double riser. So the reality is, if we want to change it to a single, we're going to get that notification again. So let's increase it to 40%. And it's basically saying that the minimum oil return was 27. So it was just a shade over what we'd class as the absolute aspirational. Now, that for me is good enough, because this is where the experience comes in. In low loads, you might get residual amount of oil which you're not getting back up. But let's face it, this time of the year, unless something's on a defrost, which there will be, you know, you've probably got 1 case at any one time on a defrost, but the other 3 cases are probably running, and the duty that's going through that oil riser is probably 75%. So if I just go back through, so what's happening here is, as I say, something I'm going to fix everything here, and what I'm going to show everybody is I'm going to fix all these suction terminals to get rid of the oversized line, because generally speaking, if we're quite honest with ourselves, we've probably, these cabinets are probably on 7/8 connection tails.
So this is the first time I've actually seen it. So when you're clicking on fix and fix all, is it fixing all of the issues programmably through the entire pipe work?
Hey John, what it's doing there, when you fix that padlock, if I select fix all, it's fixing everything at the diameter that the software's calculated at.
Okay.
So you can fix individual things, and that's actually quite a good thing. If you're adding load or you're adding cases at a later date, you can actually say, well, I've got to overcome this riser. I don't want to put a new riser in. My riser's Incheon 1 for arguments, for example, and we're connecting a couple more cabinets. We can actually see the consequence of having to work around existing pipe work.
Are there pre-selected recommended standards as soon as you open the software? You know, similar like when you run a compressor program, they'll have certain defaults in there when you pick your compressors, just like say optimal. Does MicroPipe have something like that?
No, it doesn't. No, so
Okay.
so you need to have that experience when you put in those design entries in, John.
Okay.
So what I'm going to do though, John, did I send you the installation notes and things like that?
You did.
Yeah. What I'll do, and it's an offer open to everybody, but anybody who specifically wants these files and the presentation pack, just let me and Trevor know. I'll send the calculations across so you can actually open it in your own MicroPipe software.
That'd be great.
No problem. Let's run. So hey, look what it's done. This has surprised me. Hey, it had just taken it to 1.05. So fixing the 7 load ends from Incheon 1 to 7/8, which is probably what we're going to see in real life. But I'm happy. I've got a reasonably well-designed suction line here. So I'm going to save this. As I said, I'd already done this, so so Trevor, how long have we got on this session?
We have another 3 minutes.
I'm going to go through the low temperature suction. I think the common liquid line, I think we pick up next week. But this is good because there's been a lot of good, interesting questions and dialogue today. Starting off, if we recall back at the presentation, we've only got 3 cabinets. I've got effectively 7 circuits. So 3 cases building back to the medium to the low temperature side, so the low temperature compressors of the package rack system. I've assumed duty of 3 kilowatts on each cabinet. So if we go to the last circuit, we're carrying 9/8. We've got a pipe size of 1.3" with a velocity of 13.32, which is actually quite high. I've got a maximum penalty set here of 1.96. So if we look at the design entries, so evaporating temperature fine, maximum penalty, I've put in at 2. So say, well, let's set this at 3 as well. And let's run. Hey, what's going on here? I must have hit liquid first because it was telling me I had no information. So we've got a maximum penalty of 2.37, which is almost half a Kelvin out of where we'd ideally want to be. So first thing I would look to do here is let's just fix everything. So if we have a look at the tail ends here, got quite a high suction line velocity there, to be perfectly honest. So I'm going to go in, I'm going to fix that 1.1 because it's low temperature as opposed to high. I'm going to set this at 1.1. And that's interesting, that will go back. So I'm going to set that 1.1 too. So we're saying it's slightly over, but look what the impact it's had on the system penalty of 2K. It's brought it down by half a K by just doing that. So if I've got now 2 terminals next to each other, 1.1, but 3, this is a horizontal section of pipework. That to me, that's quite a high velocity. Now MicroPipe saying that's absolutely fine, but I'm going to fix this one, 1.3. As we can see what it's doing, we're actually reducing now the penalty. So I know that 4's a terminal, 5. That's quite a high velocity for a horizontal line. If I fix that, run the calculation again, hey, we've dropped the penalty even further. 6, I've got a double riser here. I'm going to unfix this. Let's see what it fixes. So it's fixed at the same, and it's telling me now 2.37. And the final circuit, I'm going to go back to circuit 6, everybody. So I've got 13.59 meters per second. I'm going to increase that to 1.5 and see what the effect is. So we're down now at 1.82, which is absolutely great. We're within the 2 Kelvin penalty. Now we've only got 3 cases here. I haven't actually run this yet as a single. So let's see what can happen. I'm going to fix everything. But the one thing I'm going to unfix this riser, and I'm actually going to see. Let's see what happens. 33% all return. I've got 3 cases connected into that riser. Yes, it doesn't like it. Now I could play around with this, and this is why double risers at times are so important, especially on low temperature systems. What I've done there is I've set the minimum oil return at 80%. It's actually stating on an 1" single riser, it will return at 34%. That velocity is high, but even more so, we've got a hellish penalty there of 2.58. I'm going to go back. I'm going to set it at 2. It's going to force the system. It's not going to calculate. Oh, it is. I'll tell you. So let me keep this at 1" as it was. So fix that at 3. Let's run. So we're getting a good velocity now, good penalty, but look at the minimum oil capacity, it's 58%. So effectively, to get minimum oil return, we're assuming that 2 cases of the 3 are going to be running at any one time. I want to drop this down to 33%. It ain't gonna work at that. So as a design engineer, I now know, having looked at all this, so some designers may take a more pragmatic approach and say, I'm going to put a single riser in. You know, all things being equal, when things come off a defrost, we're going to get that oil back. But I'm thinking about efficiency. I'm thinking about, let's make a service technician's life easy. So I've selected it. So I'm going to unfix that line. I'm going to select a double and I'm going to run. And we're back to where we were. But look at that penalty. We've got a 1.78k penalty. So effectively, we've got, in my opinion, a well-designed suction pipe network there.
James, is there any time when you would have, say, 3 cases, because you always want it, like if there's only 1 case running, you want that 33%, so it's going to get that oil back. Is there any time where you would go and say you had that 58% and oil riser, or so oil riser minimum duty, and have to do that? Do you know what I mean?
Yes, I do. And what I can say, Trevor, is, you know, the difficulty here is when pipe work's hidden from view, let's be quiet, especially in the UK, you know, technicians on a night time, they're gonna look and they're gonna think, really, these are experienced people, but they won't necessarily think, well, I can just put 1 vertical line in here and it's going to get the oil back. But what they're not necessarily appreciating is this, when we're talking specifically around oil return and getting it back, because I'm looking at getting it back throughout all seasons. So not just in the summer months where actually 58, 60, 70, 80% oil returns, you're going to be pretty good. But one thing I would say is, due to defrosting, we do a lot of defrosting on demand in the UK, and we've shifted a lot of defrost patterns to when energy is a little bit cheaper as well, especially on frozen, where we're using electric heaters effectively. So there's ways around what we've been talking about, but for me, this is how I would design. So where I was going with this is the lowest minimum duty I would ever give, even if I've got 8 cases on that run, would be 25, because in a 24-hour period, generally cabinet and the duty is based on an 18-hour run time.
Thank you.
So I think I've done a lot of talking, so apologies, and slightly run over on
Awesome.
time.
No, and it's good. Like I continue to learn each time to get a better understanding on the engineering side, because this is very important. Is the sizing of these pipes make a huge amount of difference, and I'm really looking forward for the next one, talking about how we can make the system more energy efficient by that piping design.
Mhm.
You know, and that's a huge thing that I know we talk about efficiency everywhere, but if you can understand how that pipe work and you design it properly to make a system more efficient, I'm excited to learn about
Well, in
that.
some respects, that's exactly what we've been doing sort of this
know.
evening as well, because I become quite pedantic when I'm using the software, Trevor. So if I had a UK engineer next to me, UK designer, they would probably roll their eyes at me when I'm selecting double risers in this instance, because they know, you know, like an install tech, let's just put a single in. You know, it's going to be a cheaper install, and actually we're always going to get that oil back as long as, you know, that's the argument that they would give, but we're going to increase the system penalty. So I love to design. I like to see that penalty there, 1.78. There's only so far you can push with a low temperature system, but medium temperature, I like it as low as possible, because that's going to benefit everybody in the long run.
Awesome, James. Excellent. If anyone has any questions, you can throw it in the chat or unmute yourself. James, I want to thank you once again for this knowledge session. I keep learning, so it's fantastic for me.
Yeah, I just want to thank everyone for taking time out of the day or their evening. You know, it's especially this time of year, we're all so busy. You know, it's in the UK, we don't get that much nice weather, and a lot of people, you know, so thanks to Adita, you know, a lot of people would rather be in the gardens, chilling out, having a beer, whatever, at this time of day. You guys who are over in North America, you guys, it's 2 o'clock now 3 o'clock in the afternoon. I know how busy we all are in summertime.
Awesome, James. Thank you so much. Thank you, everyone.
Thanks, guys. This was awesome. Thanks, James.
Thank you. Thanks, John.
Thanks,
everyone.
Trevor. All right. Have a good one.
Bye.